Hello there, and welcome to the Whispering Science, your quiet companion for gentle journeys into the wonders of our universe. Tonight, we venture into a topic that, while wide as the cosmos itself, is delivered here in the calmest possible way: the tantalizing idea of parallel universes. Now, I do hope this isn't too interesting that it keeps you awake, but if it does, well, at least you'll have learned something fascinating about the great mystery of parallel realities. And just maybe, when you drift away, your dreams will carry you through infinite other worlds your waking mind has only glimpsed. Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. It's always lovely to imagine the shared quiet curiosity echoing through the world as the night deepens. So settle in, get comfortable, and let's begin our quiet voyage into the science and wonder of parallel universes. Are other realities really out there? What does science say? And could they already be brushing up against our own world? When you hear the phrase parallel universes, you might imagine countless versions of our own world, each spinning away somewhere in the darkness, perhaps almost identical to ours, or so alien as to be unrecognizable. It's a concept that sparked science fiction for generations, inspired ponderings late at night, and, as we'll learn, even earned the attention of serious, sober-minded scientists. Tonight we'll drift calmly and carefully through what these ideas actually mean, and where the real science lies among the speculation. We'll begin with the most basic question: what do we mean when we say universe? That might seem simple, but it lies at the heart of whether parallel universes could exist at all. Then, we'll float through the long story of how human beings, from ancient mythmakers to modern physicists, have tried to make sense of the cosmos, and how the multiverse slipped from imagination into the front lines of scientific debate. We'll wander through quantum mechanics, the strange and counterintuitive science of the very, very small, which accidentally led to some of the most robust ideas of parallel realities. We'll learn about cosmic inflation, bubble universes, and the dizzying possibility that even empty space might hide infinite realms completely separate from ours. Perhaps most exciting or unsettling, we'll explore whether these parallel universes could ever touch us, or if they're truly unreachable, forever just out of our observational grasp. Are there traces already lying quietly in our cosmic background, waiting for a bedtime scientist to explain them? We'll look at the sometimes spooky, always fascinating evidence, or lack of it, for other realities brushing up against our own. So as your eyes grow heavy and your thoughts soften, imagine yourself traveling deeper and deeper into a gentle, star-speckled ocean, where every twinkling point of light might just be another universe, another chance, another story waiting for a calm mind to wonder. And as we float through these scientific possibilities tonight, let curiosity be a gentle lullaby, letting fact and wonder guide you toward peaceful rest. As we embark on this calm exploration, let's gently clarify a foundational question. What exactly do scientists mean when they say the universe? The answer isn't as straightforward as it might feel when we gaze up at the night sky, sensing infinite stars glowing overhead. In the vocabulary of science, when we refer to the universe, we are usually talking about all of space and time, and everything within it. Every atom, every galaxy, every law of physics, every whiff of cosmic background radiation left over from the Big Bang. But even this definition contains some subtlety. Astronomers sometimes distinguish between the observable universe and the universe as a whole. The observable universe is everything we can see or could in principle detect, limited by the speed of light and the age of the cosmos, about 93 billion light-years across, at last estimate, though the universe itself may be much, much larger. Light from more distant regions simply hasn't had time to reach us yet. Those parts, if they exist, are beyond our cosmic horizon, tucked away in a darkness our instruments can't penetrate. And yet, for some physicists, the universe means even more. The totality of all that exists, everywhere and everywhen. This notion encompasses not only what we might observe, but also what lies forever outside our reach. Regions so far away, or conditions so radically different, that even the wildest cosmic relay couldn't bring their light to our eyes. So, where do parallel universes enter this picture? Well, the word parallel implies coexistence, other realities that unfold alongside our own. But for that idea to have any scientific meaning, we need to be precise about what could, even theoretically, be beside our universe. Are parallel universes just more space and time, stretching beyond our cosmic horizon, but essentially like our own, maybe with a star or a planet similar to Earth lying unimaginably far away? Or are they far stranger with different versions of physics or branching timelines caused by quantum choices? To keep things concrete, let's use a simple metaphor. Picture the universe as a vast, shimmering ocean. The observable universe is our small circle of lantern light on that ocean's surface, everything we can see, feel, and learn about. But the ocean itself may go on and on, far past our little glowing island. Other universes, in this metaphor, might be other patches of light, far over the horizon, or possibly different oceans altogether, separated not by distance, but by the very rules that govern them. Over the last 100 years, as our understanding of cosmology has deepened, the scientific meaning of universe has grown more nuanced. Our own universe, by best estimate, is about 13.8 billion years old and filled with hundreds of billions of galaxies, each with hundreds of billions of stars. That alone is awe-inspiring, yet modern theories allow us to consider that even this vastness might be, in some sense, only a single drop in a much larger cosmic sea. When scientists entertain the idea of parallel universes, they're considering that there could be other entireties like ours, governed by similar or perhaps entirely different physical laws. Sometimes these universes are suggested to lie immeasurably far away in space. Other times, they're viewed as separate cosmic bubbles, never touching, or as the outcome of branching possibilities, where every choice, every quantum flicker, spawns a new version of reality. This isn't a matter of science fiction. Even our most proven and practical theories, such as quantum mechanics, general relativity, and inflationary cosmology, hint, however subtly, that our universe may not be the only one. The possible existence of other universes with unique histories would have profound implications. For one, it would transform how we think about our place in all that is, reminding us gently that even the familiar starry sky above might be just one beautiful expression among many. And so, as you rest comfortably tonight, remember that when we use the word universe in this gentle bedtime science, we're talking not just about all that we know, but perhaps all that can be in forms and places we're only beginning to imagine. Our calm curiosity will let us wade, lightly but scientifically, into the question of whether more realities are waiting beyond the reach of our instruments, or just a possibility away, quietly existing in the vast stillness that surrounds our own experience. As we explore further, we'll see how the story of other worlds began long before telescopes or quantum experiments, a story shaped by human wonder as much as by scientific discovery. Now let's gently drift back in time, to the earliest glimmerings of curiosity about other worlds, and see how humanity's fascination with realities beyond our own first took root. Before the formal methods of modern science, our ancestors looked to the star-laced darkness above and wove tales of countless realms, some above, some below, some right beside our own, forever hidden behind veils of magic or mystery. In many ancient cultures, the notion of parallel worlds or layered realities played a central role. The Norse, for example, envisioned Yggdrasil, the world tree, a cosmic structure branching into 9 distinct realms, each with its own inhabitants, destinies, and governing rules. In Hindu cosmology, the vast universe cycles through infinite creations and destructions, sometimes envisaged as multiple planes of existence stacked atop one another. Even the ancient Greeks mused about myriad worlds. Democritus, for example, lived around 400 BCE and speculated about countless worlds, differing in size, some with no sun, some with no moon among them. These stories weren't science in the modern sense, but they reflected a deep longing to understand what lay beyond the obvious, and to grapple with the odd, persistent feeling that what we experience might not be all that is. From the Aboriginal Australian concept of dream time, a timeless realm coexisting with ours, to the bountiful afterlives of ancient Egypt. History is rich with visions of hidden places just out of reach, layered over, under, or beside our own. As centuries passed and the scientific revolution dawned, explanations of nature grew more systematic. Yet the question of other worlds remained. The 16th century philosopher Giordano Bruno famously argued not just that the stars were suns, but that each might be orbited by their own worlds. Expanding on Copernicus's sun-centered system, Bruno went further. The universe, he claimed, was infinite, containing innumerable suns and innumerable Earths with living beings. His daring ideas were controversial. He was executed for heresy in 1600. But in hindsight, he planted seeds of possibility that continue to echo in today's scientific thinking. Through the lenses of ever more powerful telescopes, astronomers of the 17th and 18th centuries uncovered vast new orders of reality within what we now call our universe, other planets, swirling nebulae, and eventually entire galaxies. As each boundary of the known world was pushed outward, the idea that reality might be richer, more populous, more diverse, grew ever more plausible. By the early 20th century, Edwin Hubble's work revealed that even the Milky Way, once thought to contain all the stars, was just one galaxy among billions in the visible universe. Parallel to these cosmic discoveries, philosophers and early scientists continued to muse about the possibility, however faint, of other universes, a plurality of worlds, as some poets and thinkers phrased it. What made their thinking so enduring is that it captured something essentially human. The sense that reality could branch, repeat, or unfold in unforeseen ways, far beyond daily experience. But it wasn't until the 20th century, with the birth of modern physics, that the question of parallel universes began to move from poetic speculation into the realm of scientific theory. As relativity and quantum mechanics reshaped our picture of reality, they inadvertently opened the door to new possibilities. Space-time could be curved, infinite, or sliced into parts. The quantum world revealed multiple outcomes existing in a strange, probabilistic haze. It is important to appreciate how imagination, myth, and early philosophical thought laid fertile ground for the rigor of modern inquiry. Many scientists today, while drawing strict lines between myth and testable theory, still tip their hats to the roots of the human impulse. An impulse not just to explain what we see, but to ask what else could exist and how we might one day find it. And just as these ancient stories once brought comfort or wonder to listeners huddled by firelight, the modern questions about the multiverse can gently lull us tonight, inviting us to see our everyday world from a new, awe-filled angle, as perhaps one chapter in a much broader story. As we drift onward in this restful science journey, we'll see how modern ideas about the multiverse emerged, not merely from dreams and legends, but from attempts to answer puzzled questions left by the deepest laws of physics. Let's allow our minds to gently unfold into the scientific landscape of the 20th century, where myth gave way to math, and the concept of the multiverse began to take concrete shape. The idea didn't emerge all at once. It was built piece by piece, each edition prompted by a paradox, a puzzling observation, or a bold new mathematical insight. The early 1900s saw two scientific revolutions. First, Einstein's general relativity gave us a universe that could expand, contract, curve, and warp, whatever the cosmic rules dictated. Second, the strange discipline of quantum mechanics revealed a world of probability, uncertainty, and multiple potential outcomes, all coexisting in a sort of shimmering possibility. These theories brought physicists up against unexpected questions. For example, if space can be infinite and the laws of quantum mechanics allow multiple outcomes, then what really defines a universe? Could every outcome or pocket of space be a universe in its own right? The 1950s delivered a particularly important turning point. Physicist Hugh Everett III, frustrated with the ambiguity in quantum measurement, developed what would later be known as the many worlds interpretation. According to Everett, every time a quantum event has several possible outcomes, like a particle being in two places at once, all outcomes actually happen, each in a newly branching universe. In one, you turn left. In another, you turn right. In one, Schrödinger's cat lives. In another, it does not. This was a dramatic, controversial leap. Rather than wave away the mystery, Everett's model embraced it fully, proposing that all possible realities are realized, and the universe effectively splits each time. At first, Everett's ideas were largely ignored, even dismissed, by most physicists. His work lay dormant for nearly 2 decades before others, searching for quantum clarity, recognized its value. By then, another track had begun to emerge, one involving the origins and structure of space itself. In the 1980s, the theory of cosmic inflation changed our view of the early universe. Developed by Alan Guth, André Linde, and others, inflation explained why space appears so uniform and why galaxies are distributed as they are. But the inflationary model unexpectedly suggested a multiverse. It predicted that while our patch of space ballooned into a universe, countless other patches could do the same, each with different properties, histories, and possibilities. In this scenario, universes might be forever isolated, embedded within an ever-inflating cosmic foam. It's important to understand that, scientifically, these ideas didn't arise out of a fanciful desire to believe in the fantastic, but from sincere attempts to resolve deep inconsistencies in theory and observation. For instance, the multiverse concept offers a way to reconcile why the physical constants in our universe are so well tuned for life, a puzzle known as the fine-tuning problem. If there are countless universes, all with different values for physical constants, then perhaps ours is simply one where conditions allow life and consciousness. No miracle required, just probability at cosmic scale. Not all scientists have embraced these ideas. Critics worry that, without a way to observe or test for other universes, the concept drifts dangerously close to speculation. Interesting, yes, but not yet firmly within the grasp of science. And yet the mathematical structures that predict a multiverse arise naturally from our best physical theories. To ignore them would be to turn away from the potential of bold reasoning. Even Stephen Hawking, cautious as he was about unobservable speculation, conceded that certain models of inflation and quantum gravity make the multiverse almost inevitable. So, when we speak gently of the birth of the multiverse idea, remember, this is no single moment but a gradual coalescence, sometimes bold, sometimes controversial, of scientific creativity, theoretical necessity, and a willingness to look beyond the limits of our observable patch of sky. It is the story of minds, restless yet careful, reaching for an ever larger understanding of what reality itself might mean. Tonight, as you drift in and out of wakefulness, let yourself rest in the thought that the multiverse is not just a flight of fancy, but the result of decades, indeed centuries, of humans pressing gently against the boundaries of possibility, asking not just what is, but what else could be. In our next gentle exploration, we'll see how the sheer size and possible infinity of space further fuels the idea that parallel universes might truly exist. As we drift quietly into bigger and bigger scales, let's consider the sheer, almost ungraspable vastness of space itself. Space that might, just might, go on forever. Astronomers have long wondered, if the universe has no edge, no boundary where it ends, does that mean it's truly infinite? What happens if you keep traveling in a perfectly straight line, never turning, never stopping? The idea of infinity is comforting in a way, like a soft blanket covering everything. But it also introduces profound puzzles, especially when we start to think about parallel universes. Let's start with a calm fact. The observable universe, the part we can see, is about 93 billion light-years across. That's already a number so large as to feel almost meaningless in everyday terms, a distance so immense that light, the fastest thing in the cosmos, needs over 90 billion years to cross it. And yet, the universe itself may be vastly larger than what we can observe, possibly infinite, with regions forever beyond our reach, because the light from those places hasn't had time to reach us since the universe began. Here's where things get wonderfully strange. If space does go on forever, and if the laws of physics are roughly the same everywhere, then the matter in those distant places will eventually arrange itself in every possible way it can, simply given enough room and enough time. Think of it as a cosmic version of monkeys at typewriters. Given an infinite number of monkeys typing randomly, someday, somewhere, one will type out the complete works of Shakespeare, simply because every possible combination will eventually happen. What does this mean for parallel universes? In an infinite universe, there are so many regions, so many galaxies, so many stars, so many combinations of atoms, that you would, by chance alone, get patches that look identical to our own. Somewhere, incredibly far away, there could be another planet Earth, with someone who looks just like you, possibly tucked into bed at this very moment, listening to parallel bedtime science. It's not science fiction. It's an implication of statistics and infinity. These patches would be so distant that no signal, no ship, no photon could ever travel between us. The distances are measured in unimaginable fractions and powers. If you wrote the number down, it would stretch across the page and far beyond. The famous physicist Max Tegmark, a leading advocate for this idea, calls this the level 1 multiverse. In his book, Our Mathematical Universe, he suggests that in a truly infinite cosmos, copies of ourselves and our entire world must exist, endlessly repeated, in every possible variation. According to his calculations, the nearest exact copy of you is at least 10 to the power of 10 to the power of 28 meters away. A number so large, there's hardly any way to picture it. And yet, if infinity rules, those distant realms would be as real as our own. But does infinity really exist in nature? Or is space somehow finite, looping around or closed off in a grand cosmic shape? This is a central question in cosmology. The current evidence from measurements of the universe's geometry, especially using data from the cosmic microwave background, the afterglow of the Big Bang, suggests that space is very close to flat and might be infinite. But we can't know for sure, since we can only observe a finite region. Still, even if the universe is finite, it could be overwhelmingly vast, large enough for every possible arrangement of matter to play out somewhere. This gently nudges us toward the thought that what we call the universe might, in effect, be a patch in a far wider pattern, filled with parallel worlds separated not by any mysterious barrier, but simply by distance so great as to be, for all practical purposes, unreachable. From a peaceful scientific perspective, this grows even more fascinating when we think about the mathematics of chance. Just as a shuffled deck of cards will always produce a unique order, unless you shuffle enough times to inevitably repeat, so too the particles in the universe, given unlimited room and combinations, can and will duplicate arrangements, making true cosmic repeats not just possible, but guaranteed. It's a quietly breathtaking idea. But notice, in this scenario, parallel universes arise naturally, not from speculation about strange physics, but from the mathematical implications of infinite possibility. No new fundamental laws are proposed. It's simply that so much room allows every story to play out, somewhere in that endless stretch of space and time. As we contemplate this cosmic vastness, let it be a calm reminder that when you look up at the stars, you are gazing into a depth with no certain bottom, and that among the uncountable galaxies might lie unimaginable varieties of worlds, some perhaps not so different from ours. Now let's quietly turn our attention to the world of the very small, where quantum mechanics presents us with a different kind of curiosity, one where vastness isn't measured in distance, but in the blossoming of possibilities. As our gentle journey continues, let's shift from the almost infinite stretches of physical space to the remarkably strange landscape of quantum mechanics, the science of the very, very small. If the vastness of space can suggest parallel realities through sheer statistical possibility, quantum mechanics hints at another path, one that emerges not from distance, but from the weirdest properties of nature itself. Quantum mechanics is the theory that governs everything at the smallest scales in our universe: atoms, electrons, photons, and the fields that connect them. It rose to scientific prominence in the early 20th century, thanks to minds like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. Their experiments uncovered a world that resided beneath the surface of classical predictability, a world where chance, uncertainty, and multiple outcomes truly rule. Here's where the science becomes quietly astonishing. In quantum physics, particles do not have definite positions or velocities until they're measured. Instead, their behavior is described by a wave function, which spreads out and offers a range of probabilities for different outcomes. Only when an observation or measurement is made does the particle seem to choose a single position or path. This phenomenon is known as quantum superposition. Imagine flipping a coin, but instead of landing as heads or tails, it exists as a fuzzy blur of both headness and tailness, simultaneously, until you peak. In quantum experiments, particles like electrons can be in 2, 3, or infinitely many places at once, at least as far as the mathematics is concerned. Famously, Erwin Schrödinger illustrated this with his thought experiment involving a cat. Schrödinger's cat is shut in a box with a mechanism tied to a quantum event. If a radioactive atom decays, a vial breaks and the cat is exposed to poison. If not, the cat is safe. The twist: until someone opens the box and observes it, quantum mechanics says the atom is both decayed and not decayed, meaning the cat is both alive and dead at the same time. This thought experiment wasn't meant to be taken literally for cats, but to highlight just how peculiar quantum theory is when naively applied to the macroscopic world. This indeterminacy, this openness to multiple possible realities, led to deep debate. Some early scientists believed there must be some hidden cause, a deeper reality that determines the outcome but remains invisible to us. Others accepted the strangeness. Niels Bohr famously remarked, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." Among the many ways to interpret this strange realm, the idea of parallel universes took a particularly bold shape. If a system can have multiple outcomes, such as a particle traveling 2 paths, or a cat living and dying, then what if all those outcomes actually happen but in different original worlds? It's in this quantum playground of possibilities where the stage is set for the idea that alternate universes might not just exist out there, separated by distance, but may pry apart from one another at every act of measurement, every quantum event. This is the groundwork for the many worlds interpretation, a theory that suggests each quantum decision splits reality itself. But even if we set aside the boldness of the many worlds idea for a few moments, quantum mechanics quietly changes how we think about what's possible. It suggests the universe is not a single, tight thread weaving through time, but an expanding set of options, like a tree endlessly branching into the night. The comforting steadiness of classical physics gives way to shimmering uncertainty. Even the simplest atom is part of a kind of cosmic lottery, a haze of maybes rather than a single crisp fact. Quantum mechanics has been experimentally validated time and again. Its predictions power real technologies that shape your everyday life. Lasers, transistors, magnetic resonance imaging, even the phone or computer by your bedside, all rely on the truth of quantum principles. That means, at the core of your nightly routine, turning out the lamp, relaxing your body, listening to calming science, the ambiguity and possibility of the quantum world are quietly, invisibly at work. As you settle more deeply into calm curiosity, know that at the smallest scales of your own body and the very fabric of reality, countless possibilities hum in the dark, all allowed by the soothing, if mysterious, laws of quantum mechanics. Next, we'll gently unfold into one of the most mind-bending scientific proposals, the many worlds interpretation, where every quantum event may be a fork in the road to a new universe. Let's unravel, in our gentle and deliberate manner, one of the boldest quantum ideas ever put forward, the many worlds interpretation. This is more than just a clever story. It's a framework shaped by a sincere response to the puzzling behavior of nature, carefully crafted by a scientist seeking to restore logic to the shadowy world beneath the surface. The many worlds interpretation was introduced in 1957 by Hugh Everett III, then a graduate student at Princeton University. Everett, like many physicists, was troubled by the idea that observing a quantum system seemed to collapse its possibilities into one outcome. Why should observation or measurement, something as seemingly mundane as flipping a switch or checking a detector, suddenly change the fabric of reality? Everett's proposal was elegantly radical. What if measurement doesn't collapse the wave function at all? What if instead, Every possible outcome takes place, with each outcome realized in its own, equally real universe. In other words, when a quantum event happens, the universe branches, creating a separate reality for every possible result. So if you measure the spin of an electron that can be up or down, the universe splits into two, one in which you see up and one in which you see down. At first, this may sound extravagant, even fantastical. Imagine standing at a crossroads, every decision you face, no matter how trivial, causing the world to branch. In one universe, you turn left, in another right. In some, you never leave home at all. All these branches are equally real, running parallel to one another, but forever out of contact once the split has occurred. Crucially, Everett's theory does not require any special role for the observer. The universe keeps evolving continuously through the mathematical machinery of quantum mechanics, and in doing so, constantly creates new branches. There's no need for mysterious collapses or consciousness-driven changes, just the calm, impartial arithmetic of wave functions and probabilities. What's astonishing is that, mathematically, the many worlds interpretation makes the same practical predictions as orthodox quantum mechanics. Every experiment you can perform in a lab, every statistical result, comes out precisely as expected. In this sense, the theory is empirically equivalent. It matches what we see, though it describes the underlying truth in a far richer, stranger way. There's a quiet beauty to the proposal. Instead of a universe where the cards fall one particular way, leaving all other hands forever lost, Everett's world is one of total inclusiveness. Every quantum choice is honored, every possibility fulfilled, somewhere in the endlessly growing tree of reality. Nobel laureate Richard Feynman summed it up. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look anything like the real world. But is this really how nature works? The many worlds interpretation avoids some of the weirdest paradoxes of traditional interpretations. For example, it sidesteps the notorious observer problem, the unsettling notion that consciousness itself changes reality from quantum theory, and it suggests a deep consistency. The wave function always evolves smoothly, without special exceptions for measurement. Yet, it does come at a price some find uncomfortable for bedtime reflections. The universe, according to Everett, is constantly splitting, branching, unfolding into a stupendous number of alternate realities, each one just as real as the next. For any quantum event, the world divides, and all branches persist. If you try to picture the scale, you'll quickly discover it's beyond comprehension. Just consider your own life. Every heartbeat, every blink, every interaction at the atomic level, and in each case the universe quietly, almost serenely, multiplies its branches. Scientific debate continues even after more than 60 years. Some physicists embrace many worlds as the most straightforward interpretation. Others prefer alternate explanations that keep reality largely singular but laden with strange rules. Critics point out that the many worlds interpretation is almost impossible to directly test. The other branches are, by definition, inaccessible once separated. Supporters, meanwhile, find its logic and mathematical clarity deeply compelling. What's certain is that the many worlds interpretation reshapes our picture of the cosmos. No longer is reality something that happens to you. Instead, you are always at the center of a branching network, part of billions of threads spun out by quantum events. You are not chosen by chance. All outcomes are played out somewhere in the great, ever-dividing silent forest of reality. As you lie relaxed, think for a moment that every sigh, every turn, every quantum flicker in your own body is both utterly real here and just one of countless paths followed elsewhere. In that sense, nothing is ever truly lost. Possibility is honored without end. The night itself becomes a gentle metaphor for this quantum richness, with each moment of darkness sheltering a myriad of invisible, parallel starlit vistas. Next, let's imagine the cosmic landscape on a still larger scale, where each universe, born in the earliest throes of creation, may be its own separate bubble in the vast expanse. As you rest calmly with the notion of endlessly splitting realities, Let's now drift into an even more cosmic view, a landscape shaped not by the flicker of quantum possibility, but by the roaring expansion of the universe itself. Here, the very beginning of everything gives rise to the image of bubble universes, a concept nearly as mesmerizing as swirling soap bubbles in a gentle breeze, each floating in a vast invisible foam. To understand bubble universes, we need to revisit one of the most remarkable chapters in modern cosmology, the theory of cosmic inflation. In the early 1980s, physicists Alan Guth, Andre Linde, and others realized that the young universe, mere fractions of a second after the Big Bang, underwent a sudden, blisteringly rapid expansion. This inflationary epoch solved several cosmic puzzles, including why the universe looks nearly the same in every direction and why everything is so evenly spread out. But this tremendous idea carried an astonishing implication. As the mathematics of inflation evolved, researchers discovered that inflation itself might not have shut off everywhere at the same time. Instead, it could spawn pockets where inflation ends, each pocket blossoming into a universe, each with its own story, properties, and fate. Imagine the cosmos as an eternally frothing pot, with bubbles constantly forming, expanding and cooling, all within a swirling, foamy sea of inflating space. Each bubble in this cosmic foam could be considered a universe, potentially infinite in size itself, and possibly with laws of physics and constants different from our own. Some bubbles might be rich in matter and galaxies, others sparse and quiet. Some might have 4, 5, or more dimensions. Some, perhaps, might blink out as quickly as they form. The mechanism that seeds these bubbles is known as eternal inflation. As long as the inflationary process continues somewhere, new universes are forever budding into being. What makes eternal inflation so compelling isn't only its mathematical elegance, but also its fit with what we observe. The uniformity, the large-scale structure, and even the puzzling fine-tuning of the universe's physical laws can, in this model, be a natural outcome of having countless bubbles, each rolling a different set of cosmic dice. In some universes, gravity might be too strong or too weak, matter might never clump, atoms might never form, the conditions for life, as we know it, would fail to appear. In others, including our own gentle pocket, everything comes together just so, and here you are, considering these mysteries in comfort. Astoundingly, the mathematics suggests that these bubbles are not embedded within our own space, like distant galaxies, but are truly separated, each with its own space-time. The space between them continues expanding at unimaginable speeds, making each bubble forever out of reach to others, a true multiverse. If two bubbles do collide, the event could be so cataclysmic that it leaves a telltale mark on the cosmic background radiation, the afterglow of the Big Bang, or possibly even birth-ground structures in the universe's tapestry. And yet, from a cozy viewpoint on your own bubble, it is nearly impossible to observe or communicate with neighboring universes. The distances, and more importantly, the dividing fabric of space-time, are simply too great, the boundaries too complete. Scientists, searching for the faintest hints of other universes, look for unexplained cold spots or circular scars in the cosmic microwave background, hoping these are relics of universe collisions. But so far, all hints are ambiguous, a puzzle still waiting in the dark. If there are truly countless bubble universes, what does this mean for you? With such a model, our own universe isn't necessarily unique or inevitable. Instead, it's one successful bubble among many, a quiet room in a mansion of endless design. Our very existence, our physical laws, and everything we experience could all be accidents of cosmic inflation, possibilities given shape by the wild, ceaseless foaming of space. This view, developed barely more than 40 years ago, stands as one of the gentlest but grandest expansions of human thought. It's no longer just quantum choices, Schrödinger's cat, or a split at every turn, but the universe itself blossoming, again and again, on a stupendous scale. So tonight, as you tuck into the soft embrace of your own world, let that image of the bubble universe linger, one among many, afloat and secure in the infinite froth of the cosmos. Each bubble holds wonders and mysteries unimaginable, all contained within the silent, unseen sea of possibilities that inflation's theories have brought gently to light. Next, we'll let our thoughts hover on the mysterious idea that there may be even more, worlds hiding not in distance or branching choices, but in dimensions beyond those we know. Now, as sleep weighs gently on your eyelids, let's wander into one of the most abstract and alluring concepts in all of science, the prospect of dimensions beyond the ones we experience, a hidden scaffolding where other universes might quietly reside. For most of us, dimensions are simple: up and down, left and right, forward and back, plus the inexorable passage of time, a comforting four-dimensional tapestry we navigate every day without a second thought. But when scientists peer into the mathematics of modern physics, they sometimes glimpse far stranger structures, a reality built not on 4 but perhaps 10 or even 11 dimensions, some curled up and unseen, others vast and pregnant with hidden worlds. This intriguing notion emerges most famously from efforts to unify the laws of nature, to reconcile the two dominant frameworks of physical theory: general relativity, which rules the very large, and quantum mechanics, which rules the very small. For over a century, physicists yearned for a theory of everything, a framework that could smoothly combine gravity, electromagnetism, and the nuclear forces into a single, elegant law. The path that seemed most promising, at least for a time, was string theory. In string theory, the tiniest constituents of reality are not point particles, but tiny vibrating strings, far smaller than atoms. So tiny, in fact, that if an atom were enlarged to the size of our solar system, a string would just barely stretch across the width of a tree. Remarkably, the mathematics of string theory only works if spacetime has more than the 4 familiar dimensions. Specifically, 5 consistent string theories emerged, each one demanding 10 spacetime dimensions, 9 spatial, 1 temporal. Later developments suggested a more general framework, MA theory, which works most cleanly in 11 dimensions. So where are these extra dimensions? Why don't we perceive them? String theorists offer a gentle answer. The extra dimensions are compactified, rolled up so tightly at the smallest scales that, like the fine curl at the edge of a tightly drawn ribbon, they escape detection by everyday senses and even our most powerful microscopes. In each possible way of curling these dimensions, each geometric compactification, the physics that emerges in our extended 4-dimensional world can be radically different. Forces might split, particles might behave differently. Even the very laws that seem immutable here may shift and change, depending on the unseen structure of those hidden directions. Here's where the tapestry grows truly vast. In the landscape of string theory, there may be an astonishing number of ways for these extra dimensions to be shaped. Some estimates suggest as many as 10 to the power of 500 possible configurations. Each distinct configuration might give rise to a universe with its own set of physical laws, particles, and cosmic histories, a virtual infinity of potential realities coexisting yet fundamentally disconnected. In this picture, our universe could be just one room in a much larger mansion, what some theorists have dubbed the multiverse of string theory. Another path to hidden dimensions comes from brain world scenarios. In some versions of string theory, our entire universe is a 3-dimensional brain, short for membrane, floating in a higher dimensional space, sometimes called the bulk. While we and everything we experience are confined to this brain, gravity or exotic particles might occasionally leak into or out of extra dimensions, hinting at their presence through tiny but detectable anomalies in experiments or cosmological data. Are these speculative ideas or grounded in experiment? At present, the extra dimensions of string theory and brain models are theoretical, without direct experimental support. Particle accelerators like the Large Hadron Collider have hunted for evidence of extra dimensions, such as the fleeting creation of microscopic black holes or missing energy from particles escaping into hidden realms. So far, the search continues, gently nudging at the boundaries of what's possible to see with the tools of modern science. Yet what is truly peaceful to contemplate is how these ideas are born from our relentless, yet quiet drive to understand the world, to unify its apparent chaos into one symmetrical whole. As string theorist Brian Greene has observed, Extra dimensions might have no effect on our ordinary lives, yet they remain a gentle echo, a sign that the story of reality could be richer and more layered than we ever dared to imagine. Tonight, as you drift deeper into rest, you might picture our universe as a shining thread woven through a multidimensional tapestry, surrounded by countless others, all hidden within the folds of higher geometry. So close, perhaps, yet eternally separated by the silent rules of dimension and mathematics. And as we move quietly forward, let's wonder together. If there are other universes separated by hidden dimensions, could they ever touch us? Might the boundaries between worlds be thinner than we think? From the comfort of your pillow, let your thoughts gently linger on an intriguing and slightly provocative possibility. If other universes truly exist, whether as distant regions in an infinite expanse, quantum branches, or bubbles in a cosmic foam, could they ever collide with ours? Might the boundaries between realities be more porous than we imagine, allowing for fleeting contacts, gentle touches, or even energetic and cataclysmic encounters? This idea that universes could bump into each other has drifted from the outskirts of theoretical physics into the realm of serious scientific inquiry, inviting even the most careful minds to investigate what such collisions might look like and whether they could ever leave footprints in the sky for us to discover. Let's explore one of the scenarios where this becomes most vivid: the world of bubble universes arising from eternal inflation. As you might recall, eternal inflation suggests that each new bubble or universe is formed as inflation ends in a local patch of space, with the surrounding space still inflating wildly. But inflation, like all cosmic processes, is messy and probabilistic. Over trillions upon trillions of years, as new bubbles form and expand, it is natural to wonder, could any of them grow close enough to touch? What would such a meeting look like if you could witness it from the safety of your own cosmic dwelling? Imagine for a moment, you are in a bubble universe, subtly drifting through an endlessly expanding foam. If another bubble formed nearby, perhaps at an unfathomable distance away, but still within some conceivable reach, the boundaries between the two would begin to approach each other, stretched and shaped by whatever cosmic expansion still dominates outside. As bubbles make contact, their edge regions don't quietly merge. Instead, the differences in their vacuum energies, the deep underlying properties that define how each universe works, could collide in a cosmic event of staggering violence. The result might be shockwaves of energy, sweeping across both universes' boundaries, altering the fundamental physics in the affected regions, disrupting galaxies, and even erasing structures formed up to that point. Would such a collision be survivable? For the inhabitants of these universes, if there are any, the answer is likely no. The event would be rapid and energetic, marking the ultimate reset. But here's the captivating gentleness science offers. Such collisions are almost unimaginably rare on human timescales. The ever-accelerating expansion of space serves as a buffer, stretching the regions between bubbles apart, making direct contact less likely with each passing epoch. For those of us in our own universe, the real question is, could any evidence of a bubble collision be detected even billions of years after the fact? Scientists have proposed that if our universe had bumped into another bubble sometime in its deep past, the collision might have left a telltale pattern in the cosmic microwave background, the faint afterglow left when our universe emerged from its own hot beginnings. A collision might leave circular scars or cold spots, regions where the energy and conditions are subtly different due to that ancient universe-altering event. Over the past 2 decades, cosmologists have pored over the cosmic microwave background data gathered by satellites like WMAP and Planck, looking for precisely these anomalies. Some small features, such as the cold spot in the southern hemisphere of the sky, have sparked speculation. Could this be a shadow, a birthmark from a time 2 universes brushed like soap bubbles on a cosmic river? Yet the evidence so far is ambiguous. The cold spot and other candidate features may be products of statistical chance, or the subtle fingerprints of structures within our own universe. The data gently resist a strong conclusion, keeping the matter delicately balanced on the knife edge between hope and skepticism. Parallel to the bubble collision idea are wilder but scientifically meaningful proposals from string theory and brain world models. In brain collision scenarios, our universe could be a three-dimensional membrane floating in a higher dimensional bulk, with other brains passing nearby. Some theorists have even speculated that the Big Bang itself might have been triggered by such a collision, an ancient, universe-creating crash between multidimensional worlds. Again, these ideas sound fantastic, bordering on the science fictional, but they grow naturally out of attempts to unify quantum theory and gravity. The mathematics involved isn't just playful abstraction. It comes with equations, predictions, and the hope for traces in the cosmic data. If collisions between universes or brains did happen, they might not only leave background scars, but also create gravitational waves. The gentle ripples in space-time first observed in 2015 by the LIGO and Virgo observatories. While the gravitational waves we've detected so far have emerged from merging black holes or neutron stars, some researchers hope that future, much more sensitive detectors might someday register an undulating whisper from a universe-altering impact. For now, all evidence points to our universe being isolated, its boundaries quiet and unblemished. But even tonight, thoughtful researchers continue their quest, scanning the sky for that singular sign, a subtle pattern, a barely perceptible disturbance that hints other universes have brushed past ours, leaving a cosmic fingerprint behind. As you rest, consider the delicate possibility that universes may be forever separated by unimaginable expanses. Yet in the vast theatre of all that is, occasional gentle traffic may have echoed in the night, reminding us that our reality could be just one performance in an infinite and interconnected cosmic ballet. Next, let's step back and consider what actual evidence we have, or don't yet have, for these extraordinary possibilities. Now let's exhale and settle calmly into the heart of scientific thinking. What evidence, if any, points toward the existence of parallel universes? After all, science proceeds not by imagination alone, but by careful observation, reproducible results, and the willingness to let nature's data steer our beliefs. The idea of other universes is among the most profound questions we can ask. So where do we look for hints, and what have scientists actually found? First, it's important to understand the challenge. By definition, if a parallel universe is truly separate, no matter whether it's hiding far away in the cosmic foam, unfurling as a quantum branch, or wrapped inside hidden dimensions, it should be fundamentally unobservable from within our own. This is what makes the hunt so delicate, so much like searching for a gentle breeze in a still, closed room. If any evidence exists, it would have to come from subtle fingerprints, disturbances, or patterns slightly at odds with what we would expect in a universe untroubled by parallel neighbors. Cosmologists have spent decades searching the cosmic microwave background, CMB, that faint afterglow permeating the universe, for signs of something unusual. Perhaps a bruise left behind by a bubble universe collision, or a cold spot where the laws of physics might have momentarily shifted. As mentioned in our previous reflections, certain features such as the famous cold spot have attracted attention. While some researchers floated the idea it might be a mark of a cosmic collision, most analyses indicate it is simply a natural fluctuation, a statistical oddity that fits within the probabilities we know for random patches of space. Beyond these temperature anomalies, scientists have studied the polarization of CMB light, looking for swirling patterns, called B-modes, that might hint at gravitational turbulence from epochs even before our own cosmic inflation, possibly a ripple left by a collision or contact. To date, though, these investigations have not turned up definitive signals attributable to other universes. Meanwhile, in the controlled environment of particle physics, some researchers have looked for hints of extra dimensions or parallel branes in high-energy collisions at the Large Hadron Collider, LHC. The hope is that if extra dimensions exist, as suggested by string theory, particles created in the collider might occasionally disappear, leaking away into universes inaccessible to our detectors, or that miniature black holes, possible only in higher dimensions, would flicker briefly into existence. While the LHC has produced a treasure trove of discoveries, like the Higgs boson, No anomalies ascribable to parallel universes have been observed to date. Yet the search continues with greater precision and new upgrades in the years ahead. Another investigative path involves the fabric of space and time itself. If parallel universes, or brains, move and interact in a higher dimensional bulk, they might generate primordial gravitational waves, echoing softly across the cosmos. Experiments like LIGO and Virgo are tuned for these whispers. While they have heard the crashes of black holes and neutron stars, no telltale signals of universe collisions or brain impacts have emerged. Gravitational wave astronomy is, however, in its infancy, a gentle science promising deeper cosmic hearing as technology advances. Quantum physics, too, offers subtle terrain for evidence. Some have speculated that unexplainable quantum fluctuations or the mysterious process of quantum decoherence, when systems lose their quantum weirdness and become classical, could indicate communication, or at least correlation, with other branches of reality. However, quantum mechanics as tested in the lab fits perfectly within a single universe model. No clear anomalies point to outside influence. Perhaps most tantalizing are efforts to identify dark flow in the movement of galaxy clusters, unexplained large-scale motions that might, in theory, be gravitationally tugged by masses outside our visible universe. Initial hints of such flows were reported in the late 2000s, sparking speculation about parallel universes as the culprits. Yet, more recent and precise measurements have failed to confirm these flows, suggesting that earlier data may have been artifacts or misinterpretations. All this careful searching brings us to an honest pause. As of now, there is no direct evidence for parallel universes. Every leading candidate explanation, every cold spot and fluctuation, has so far folded neatly within the tapestry of our known universe when examined with scientific rigor. That, though, does not make the search futile. If anything, it demonstrates the honesty and openness of science, always willing to search, always ready to question, and always prepared to accept nature's gentle verdict, whether the answer is comforting or contrary. Yet absence of evidence is not evidence of absence. The cosmos could still hold subtle signals just beyond our reach, or there could be clever, as yet unimagined ways of opening communication with realities just on the other side of a cosmic veil. So tonight, as you rest within the security of our own universe, let your curiosity remain undimmed. Science proceeds with patience, ever expanding our tools for questioning what's possible, with new experiments, telescopes, colliders, and observations inching ever closer to the faintest hints of something more. Now, let's drift quietly to the most mysterious and quantum of connections, the phenomenon that Einstein himself called spooky action at a distance, and ask, does quantum entanglement hint at hidden links between realities? Let's ease our thoughts into the delicate territory of quantum entanglement, a phenomenon so strange and fascinating that even Albert Einstein, himself a master of theoretical imagination, called it spooky action at a distance. This isn't just scientific poetry. Entanglement is a verified aspect of quantum mechanics, and beneath its spooky reputation lies a genuine question. Could this mysterious linkage between particles suggest a bridge, however faint, between realities or even parallel universes? To begin, let's gently revisit what quantum entanglement means. When two or more particles are entangled, their properties become deeply interwoven, no matter how far apart they may travel. If you have an entangled pair and you measure a property of one, say its spin or polarization, the outcome of the other, however distant, is instantly set, even if they are separated by light years. Imagine sending one particle across the universe and keeping one at home. As soon as you check the property of your particle, you know the state of its partner instantly and without any apparent signal passing between them. This phenomenon was first formally described in the 1930s by Einstein, Boris Podolsky, and Nathan Rosen, who proposed it as a paradox, a way to show that quantum mechanics must be incomplete, or at least hiding deeper realities. They believed there had to be hidden variables, undetected factors lurking beneath quantum theory that would restore a more intuitive, local idea of reality. Niels Bohr, the leading defender of quantum mechanics, disagreed. arguing that the world at its deepest level was simply non-local, inescapably intertwined in ways we cannot visualize classically. The paradox remained unresolved until the 1960s and 1970s, when physicist John Bell proposed an ingenious test, now known as Bell's theorem. If there were hidden variables, he argued, certain experimental outcomes would be limited in a way that pure quantum mechanics would not be. Successive experiments, most dramatically since the 1980s, have consistently shown that entangled particles exhibit correlations stronger than any possible local theory would permit. The verdict: quantum mechanics stands and entanglement is real. This truly means that entangled particles are linked in a way that transcends ordinary cause and effect, though no usable information actually travels faster than light. But what does this have to do with parallel universes? Here the conversation becomes subtle, gentle, and fiercely debated. In the standard quantum view, entanglement represents a fundamental unity. Particles share a wave function, behaving as a single system, even when separated by vast distances. There's no need in this interpretation to invoke other universes. The mathematics explain everything within our own reality. No signals, no hidden bridges, just the incredible richness of quantum superposition. However, in the many worlds interpretation, which you'll recall, posits that each quantum measurement branches the universe. Entanglement takes on an extra layer of meaning. Before a measurement is made, the entangled system exists in a superposition, with all possible outcomes gently humming in potential. When a measurement occurs, the universe branches. One version experiences one outcome, another version sees the other. In this reading, entanglement doesn't transmit information between worlds, but rather organizes the branches, ensuring that measurements stay neatly correlated. If you measure up here, you are guaranteed to find down in the corresponding parallel world. The opposing properties don't travel between universes, but arise from the structure of branching itself. Some scientists and science communicators enjoy speculating that entanglement, because it's so mysterious, might hint at deeper connections between parallel realities, or even serve as a kind of communication channel between universes. To date, there is no experimental evidence to support this more adventurous possibility. Entanglement does not allow information to pass between universes, or even between distant parts of our own universe, faster than the speed of light. Its value is at least as understood now, strictly in the correlations it produces, not in any magical transfer across universes. And yet quantum entanglement is at work all around you at this very moment. Entangled states form the bedrock of quantum computing, delicate emerging machines that promise to outstrip classical computers by orders of magnitude. Entanglement also lies behind quantum cryptography, a new form of ultra-secure communication. These are deeply practical offshoots of a phenomenon that, at heart, remains so deeply mysterious, most physicists would hesitate to claim they understand it in the ordinary sense. Perhaps what's most soothing about entanglement is that it reminds us of a hidden unity at the bedrock of reality. Whether or not it hints at links between parallel universes, it demonstrates that our world is stitched together by invisible threads, connections that persist over any gulf, however wide, defying the tidy boundaries we might wish to impose upon the cosmos. As your breathing slows and bedroom shadows lengthen, let that gentle marvel linger. Somewhere, a pair of particles separated by half a universe are quietly connected, dancing in a correlation that science can predict, but imagination alone can fully embrace. Now, let's venture into an even more provocative realm. What if the universe itself is not an objective reality at all, but a grand simulation, one among countless others? Let your mind drift now into a territory where science and philosophy intermingle, a thoughtful, provocative hypothesis that has become strangely popular in both academic and popular circles. What if, rather than existing in a single, natural physical reality, we inhabit a digital simulation? What if our universe is, in some sense, a sophisticated computer program, one of many simulated realities running in the background of a higher-level realm? Though it may sound at first like a plot twist from a late-night film or futuristic novel, The simulation hypothesis is a genuine topic of debate among philosophers and physicists, drawing attention to the question, could our universe be just one of innumerable digital worlds? This idea was brought into the mainstream by Swedish philosopher Nick Bostrom in the early 2000s. In his influential 2003 paper, Are You Living in a Computer Simulation?, Bostrom proposed what's known as the simulation argument. He reasoned, using basic principles of probability and technology, that one of the following propositions must be true. 1. Almost all civilizations at our level of technological development go extinct before creating advanced simulations. 2. Advanced civilizations aren't interested in creating ancestral simulations, simulations of conscious beings like us. Or 3. If advanced civilizations do run such simulations, then the number of simulated conscious beings would vastly outnumber the original biological consciousnesses. If that's the case, then statistically, it is much more likely that you are in a simulation than in a base-level reality. Why would anyone take this hypothesis seriously? Part of the answer lies in the fantastically rapid progress of computation. Not long ago, the idea of simulating even a few atoms across time seemed daunting. Today's supercomputers and emerging quantum computers can simulate millions of interacting particles, small portions of living cells, complex economies, and even portions of human brains. Extrapolate this ability a few centuries into the future, and the idea of simulating convincing conscious worlds does not seem so far-fetched, at least in principle. Physicists have, from time to time, speculated that certain odd properties of our universe could be signs of digital underpinnings. For example, some have wondered whether the fundamental constants, the pixelation of space and time at the smallest scales, the Planck length and time, or quantum uncertainty, could be evidence that we are living in some sort of digital hardware with limits, glitches, or computational rules. Studies have sought to detect signs of digital granularity in the cosmic microwave background, or look for evidence of pixel-like behavior in the way high-energy particles move. So far, however, nature's laws appear smooth and continuous at every scale we can measure, with no sign of cosmic latticework or computational artifacts. If we were living inside a simulation, what would that mean for parallel universes? It opens up an entirely new kind of multiverse, not just separate stretches of space or branches in quantum possibility, but countless digital worlds, all running inside a computer of unimaginable scale. In the same way that you can run many games or simulations on a modern device, a post-human civilization could, in theory, run endless diverse universes, each with its own laws, histories, and inhabitants. There are also more deeply philosophical implications. If you are living in a simulation, does it change your experience of life, meaning, or purpose? For the simulated being, every experience, every sensation, every memory, every curiosity about the cosmos feels just as real as it would in any physical universe. In that sense, simulated realities are subjectively indistinguishable from base reality. Even more, if simulations can run within simulations, the layers could stack infinitely deep, a simulation within another, like digital Russian nesting dolls, opening yet another form of parallel universes. Most scientists opt for caution. There is, as yet, no experimental evidence or clear sign to indicate we are living in a simulation. The hypothesis, elegant as it is, remains unproven, a thoughtful philosophical challenge to our assumptions, more than an observational conclusion from physics. But its inclusion here serves to show the expanding boundaries of how we define universe and reality itself. As you drift, it is both curious and restful to realize that, digital or otherwise, your reality feels truly and deeply real. Whether our universe is one among a multitude of coded worlds, or part of a natural multiverse shaped by quantum law or cosmic inflation, every moment of curiosity and gentle wonder is a testament to the profundity and richness of existence. Let's now softly consider what it would mean for us, personally, collectively, if parallel universes truly exist, and what marvels or worries that realization might carry. Let your breath slow as we begin to reflect on the sheer marvel, mixed perhaps with a hint of unease, that comes with contemplating the real implications if parallel universes truly exist. The very notion stretches the boundaries of what it means to be alive, to be human, to find one's place in an infinite mosaic of realities, each obeying its own laws and birthing its own histories. So what would it mean for our sense of self, our future, and even our safety if these parallel universes were not just poetic speculation, but sober scientific fact? Imagine for a moment that the multiverse is real, whether as an endless expanse with Earth-like worlds repeating across the void, a near-infinite tree of quantum branches, or a foaming sea of bubbling universes with different properties and constants. The first marvel is the sheer enormity of existence. Instead of one cosmos, you would inhabit a reality where every outcome, every twist of fate, every subtle flicker of matter is somewhere realized and experienced. The cosmos would not be a solitary story, but the grand compendium of all possible tales. A profound implication, and a comforting one perhaps, is the answer this provides to the old question of why us? Why are the laws of physics so finely tuned for life? Why does our universe support complexity, chemistry, and consciousness? In a multiverse, the answer is not that our world is special, but that amongst innumerable cosmoses, only those with the right conditions for life can produce beings capable of asking that very question. It's a gentle, statistical reassurance. Life arises where it can, and countless other universes may remain dark, empty, or radically different. There are deeper philosophical ramifications too. If parallel universes exist, the concept of uniqueness transforms. Somewhere, maybe very far away in space or in a distant quantum branch, there could be copies of you, living lives that branch off at every possible decision point, some nearly identical, others wildly divergent. For some, this is a marvel, suggesting an endless landscape for imagination and empathy. For others, it might seem to diminish the preciousness of individual experience. Yet each version, by nature of its existence, is unique within its context, shaped by the sequence of events and choices that define its particular story. Now consider the dangers, at least in the speculative sense. The possibility of universe-colliding events, though immensely rare on human timescales, is a concern in some bubble universe models. If, by cosmic accident, our universe were touched by another with different physical laws, the results could be catastrophic, rearranging matter, rewriting chemistry, or even erasing all structures within reach. While current understanding suggests this is unlikely within our observable future, the thought serves as a reminder of how profoundly interconnected and sometimes precarious the cosmos can be. There are also more practical, everyday implications for science and technology. If multiverses exist in the form suggested by quantum mechanics, it means that the world is not deterministic. Probabilities are not just matters of ignorance, but reflect genuine multiplicities of outcome. This has real application in quantum computing, where harnessing the simultaneous existence of many states, or branches, allows for extraordinary computational feats. Technologies born of quantum strangeness, like ultra-secure communications, quantum simulations, and sensors, are direct descendants of a worldview that, whether or not you accept many worlds, embraces radical possibility at its core. Intellectually, the acceptance of a multiverse would be a humbling step. It would decenter our cosmic story, dissolving the illusion of being at the unique center of all that exists. But instead of loss, many scientists and philosophers see this as the cosmic equivalent of growing up, trading the comfort of uniqueness for the awe of belonging to something vaster and far more mysterious than once suspected. And emotionally, what does this mean as you gently prepare for sleep? The knowledge that reality could be so much richer, that every act, every dream, and every possibility has its place, need not inspire dread. Instead, it invites a greater curiosity, a gentle marveling at the immensity that embraces all things, including you, here and now, alive at this singular intersection of time and space. Let's now softly approach the idea that perhaps, in some corner of a parallel universe, there exists another you, a doppelganger exploring different choices, living out other dreams. Allow your thoughts to settle softly around an especially intriguing, perhaps even unsettling question. If parallel universes are real, could there be other versions of you living out different choices and destinies? The idea of doppelgangers, alternate selves unfolding alongside us in quantum branches or distant cosmic realms, is a concept that plays gently with the boundaries of personal identity, fate, and free will. Let's start with the many worlds interpretation of quantum mechanics. Every time a quantum event occurs with more than one possible outcome, whether it's the decay of a radioactive atom, the path of a photon, or even, in theory, the firing of a single neuron, the universe splits. Each outcome is realized in its own equally real world. Stretching this to the scale of human life, every decision you make, no matter how trivial, a sip of tea or coffee, taking this path instead of that, saying hello or staying silent, might correspond to a fork in the great tree of quantum possibilities. In some universes, you pursue different friendships, careers, or paths. In others, you simply linger a moment longer at the window, watching the stars. The math behind this idea is not poetry, but the sober equations of quantum theory. Each outcome, filtered through probability, is granted its own branch of reality. The notion of quantum doppelgangers feels surreal, but its implications are quietly profound. Rather than living a solitary, unique life, you may be a single thread among countless others, each woven through a cosmic tapestry of possibility. Yet this does not diminish your individuality. Every you, in every quantum branch or distant region of space, experiences their own world as utterly singular, shaped by the unique cascade of choices and occurrences that led them to that moment. Your anxieties, hopes, and memories are nonetheless precious for having counterparts elsewhere. If anything, the idea is a gentle testament to the richness of being, a sign that in some deep way, all possibilities are embraced by nature. Mathematically speaking, the number of doppelgangers that might exist depends on the underlying model of parallel universes. In an infinite universe, as suggested by some cosmological models, the matter distribution will eventually repeat, meaning that somewhere, perhaps beyond any conceivable reach, there could be entire galaxies identical to our own, with earthly histories and human lives unfolding in ways nearly indistinguishable from yours. Max Tegmark has famously calculated that your closest identical counterpart would be so far away, more than 10 to the power of 10 to the power of 28 meters, that even the light from their bedtime would never reach you, not in the entire current age of the universe. But even without exact copies, the spectrum of variation quickly becomes infinite. Somewhere, your doppelganger chose a different bedtime story. In another, a vastly different path. Sometimes these alternate yous might differ by only a single sentence uttered, or a single heartbeat's difference. In others, they may have diverged so far as to be unrecognizable, shaped by worlds with different physical laws or histories. How should we feel about these reflections as we settle into rest? Some find the idea oddly comforting, suggesting that regrets and missed opportunities pose less weight. They are not erased, but realized in parallel elsewhere, giving meaning to every possible turn your story might have taken. Others sense a gentle haunting in the idea, as though one's own choices lose consequence if every outcome is played somewhere in the great quantum orchestra. Yet, consider this. In every universe where you are fully you, shaped by the succession of your own choices. Your lived experience is complete, irreplaceable, and unique to your own thread within the whole. Doppelgangers exist not to diminish your importance, but to highlight the richness of reality itself, a gentle suggestion that who you are is not bound to fate, but is instead honored by the universe in all its branches. The study of parallel universes in this sense is as much about personal meaning as it is about cosmic architecture. As you begin to drift, let the image of infinite selves provide a quiet marvel, a kind of cosmic empathy connecting you to all possible stories, each lived fully, none overshadowing the vivid presence of you here in this singular, gentle moment. Now, let's softly imagine how these dizzying concepts echo in the physics of everyday life, and explore why contemplating parallel universes matters even for our practical world. As you relax even more deeply, feel free to let your thoughts gently swirl around a simple, reassuring question. Why do ideas about parallel universes matter to our everyday lives? After all, whether or not an infinite multiverse truly exists, you'll still need to stretch in the morning, share a smile, sip your favorite drink, or hear the soft hum of nighttime traffic drifting through a window. Yet, in ways both subtle and profound, the logic and wonder of parallel universes quietly influence the fabric of our lived reality, the technology we trust, the mysteries we ponder, and the meaning we make of each passing day. To begin, the physics behind parallel universes is not confined safely to chalkboards or cosmic speculation. It's woven into the tools and comforts of the modern world. The equations of quantum mechanics, groundwork for many worlds and related ideas, govern the microchips that power your phone, the logic of energy grids, the laser that reads your credit card at the store. These advances grew out of grappling with the uncertainties and possibilities at the heart of quantum theory, including its branching notions. In this practical sense, every tap on a touchscreen or late-night text is a kind of gentle echo of the quantum multiverse, order and chance, working together, creating reliable patterns from fundamental unpredictability. On a more philosophical level, the contemplation of parallel universes invites a kind of humility and perspective rarely found elsewhere. The possibility that there are other yous or other Earths does not erase your uniqueness, but it softly refocuses the lens through which you see your story. It becomes easier, perhaps, to be gentle with yourself, to accept missteps and regrets as part of a vast branching structure, not as a single deterministic thread. You are, in this view, one blossom on an unimaginable tree of outcomes, each branch treated with equal dignity by the universe. Even the idea that other laws are possible, that somewhere, a slightly different constant, a heavier electron or a weaker gravitational pull, produces a radically different reality, can teach us to cherish the particulars of our own existence. The conditions that allow you to listen, breathe, and wonder are not inevitable. They are precious results of profound cosmic fortune, even if repeated elsewhere in the cosmos or multiverse. This awareness can be a quiet invitation toward gratitude, a sense that each night sky, each gentle moment, is the product of both enormous odds and infinite room for possibility. For scientists and innovators, the multiverse frameworks inspire creativity and exploration. Quantum computers, for instance, build on the idea that a bit of information can embody simultaneously both yes and no, mirroring the logic of simultaneous possibilities realized in many worlds. The strange entanglement that so mystifies philosophers powers the security of quantum cryptography, safeguarding information in ways unimaginable just a generation ago. The technologies of tomorrow, sensors a trillion times more sensitive, computers that guess at 1,000,000 outcomes at once, are real-world fruits grown from the tree of parallel universe thinking. Perhaps even more quietly, the multiverse gently shapes the kinds of questions children and adults dare to ask. Could there be another Earth somewhere, where another child is looking up at a slightly different moon? Did the universe have to be this way? What's out there, just beyond what we can see? By refusing to force simple answers, the study of parallel universes keeps the spirit of wonder alive, resisting the temptation to close off curiosity just when it is most needed. So, even as you drift into the soft cocoon of your bed, know that these ideas, however far-flung, circle back to the deepest realities you experience each day. They remind you that your world, with its joys and challenges, is both uniquely yours and a marvelous echo in a wider song of possibility. The science of parallel universes may never change the necessity of brushing your teeth or tending your friendships, but it might graciously add a gentle shimmer of awe to each routine, the sense that every familiar moment is also, in some quiet sense, part of something vast, bold, and ongoing. Now, as our scientific journey grows even more restful, let's turn to what we still do not know, the mysteries that remain, and the gentle hope of future discovery. As your breath becomes slower and deeper, let's peacefully reflect on an essential truth at the very foundation of science. For all we have learned about parallel universes, there is so much we still do not know. This gentle admission isn't cause for frustration, but rather for comfort and inspiration. It is a sign of the vastness and subtlety of nature, a reminder that every new answer opens countless new questions, and that curiosity can forever be your companion in both wakefulness and rest. Perhaps the greatest open mystery is empirical. Do parallel universes exist at all, or are they just products of brilliant but speculative mathematics? While the frameworks of quantum mechanics, cosmic inflation, and string theory all allow, or even suggest, parallel realities, no experiment yet has provided ironclad evidence. All searches for fingerprints of bubble collisions, echoes of extra dimensions, or vanishing particles slipping into higher realms have so far come up quiet. Our universe, though filled with suggestive patterns and backgrounds, keeps its deepest secrets well. There are also unresolved mysteries about the very nature of reality. What does it mean for another universe to exist if it cannot, even in principle, interact with ours? Is the many worlds interpretation an accurate portrayal of the quantum world? Or is it simply a useful way of keeping the math neat? Could universes be nested, simulated, or spawn new ones through black holes, as some theorists have speculated? The edges of current knowledge remain blurred, dissolving under the gaze of even the most careful thinkers. Then, there's the puzzle of testing these wild ideas. Some theorists hope that ever more sensitive observations, gravitational wave detectors, future particle accelerators, even subtle astronomical surveys, will reveal shadows of other realities. Others believe that some questions may reside forever beyond observation, resting only in the realm of philosophy and informed speculation. Meanwhile, the search for a theory of everything, a single framework that links gravity and quantum mechanics, continues. The answer to whether parallel universes exist may be hidden in this ultimate theory, a structure that unifies all the forces and particles, and perhaps quietly contains the possibility of multiple realities within its solution space. Even in the quantum realm, foundational mysteries persist. The question of whether wave function collapse truly occurs, or whether the universe simply branches endlessly, is not yet settled. Experiments test the limits of superposition, with objects as large as molecules, maybe even viruses, but so far the boundary between the quantum and classical worlds remains indistinct. For the scientific community, these uncertainties are not a mark of defeat, but a gentle call to adventure. Each unexplained anomaly, every cold spot, every hint of a dimension beyond, is a nudge to curiosity, a fresh invitation to look deeper. The process of discovery is itself a source of wonder, a shared path that lies open not only to the specialists in labs, but to anyone willing to listen and ask questions, even quietly, in the dark of night. For you, resting now, there is comfort in knowing that science is not a set of final answers handed down from on high, but an ongoing journey, a story half written. Every moment of not knowing is a space filled with possibility, a breathing room for dreams and future learning. As we relax further, let's meet a few of the explorers, scientists young and old, whose quiet persistence keeps the hunt for parallel universes alive. As you find yourself further drawn into restful stillness, consider for a quiet moment the human side of this great adventure. The scientists, thinkers, and dreamers who spend their lives exploring the frontiers of parallel universes. Their paths are rarely easy, marked as much by skepticism and uncertainty as by quiet breakthroughs. Yet their curiosity, the same gentle wonder that may keep you awake tonight, has shaped the scientific story of the multiverse from daring hypothesis to a cornerstone of cutting-edge research. Let's begin with Hugh Everett III, whose many worlds interpretation first cast the imagination of quantum mechanics into a literal landscape of endless realities. As a young graduate student, Everett's radical proposal was met with resistance. His ideas were considered extravagant at the time, years ahead of their acceptance by mainstream science. Everett eventually left academia for work in defense and mathematics, but his legacy quietly blossomed, inspiring generations of physicists to take quantum branching and its implications seriously. In the world of cosmic inflation and bubble universes, Alan Guth stands as an exemplar of scientific creativity. Working in the late 1970s and early 1980s, Guth introduced the concept of inflation almost by accident, in an effort to solve cosmic puzzles of smoothness and flatness in the universe. His insight, that the early universe underwent a brief burst of exponential expansion, opened the door to eternal inflation, and with it, the possibility of countless bubble universes unfolding in the cosmic foam. André Linde, furthering Guth's work, developed chaotic inflation, making the multiverse a natural consequence of the mathematics. Among string theorists, figures such as Edward Witten and Brian Greene have pursued the mysterious promise of higher dimensions. Their work, straddling the boundary between physics and pure mathematics, pieces together the picture of a multiverse shaped not by what we can see, but by the hidden structure and geometry of reality itself. Witten is often cited for turning string theory into a highly respected framework, while Greene has dedicated his career to sharing these complex ideas with the public, making the world of parallel possibilities more accessible to all. Even in the search for experimental evidence, scientists display patience bordering on the poetic. Teams at the Planck and WMAP satellite missions spent years analyzing maps of the cosmic microwave background, seeking faint but telling anomalies, cold spots, patterns and scars that might hint at the gentle brush of another universe. Particle physicists at the Large Hadron Collider, from Fabiola Gianotti to the thousands of international collaborators, continue to probe reality's smallest scales, searching for missing energy or whispering hints of other worlds. Then, there are the quantum pioneers, Anton Zeilinger, Alan Aspect, and John Clauser, among others, who have tested Bell's inequalities and verified the eerie predictions of quantum entanglement, making the reality of non-local connections inescapable. Their experiments, performed with the quiet precision of midnight watchmakers, are what move quantum possibility from philosophy into the realm of measurable fact. Astrophysicists like Laura Massini-Houghton have also contributed to the search for multiverse signals in the sky, exploring how a collision with another universe might leave its mark on the cosmic microwave background. Others, like Paul Steinhardt, offer profound challenges and alternatives, ensuring the field remains vibrant, self-critical, and open to course corrections. Behind each of these names lies a community. Graduate students spending sleepless nights debugging code, technicians perfecting detectors that will hunt for the faintest hint of the unknown, theorists building castles of mathematics to resolve the paradoxes that keep scientific hearts beating. The story of parallel universes is, and always will be, as human as it is cosmic, a monument to our persistent desire to know what lies beyond the visible, to touch the infinite, and to patiently translate dreams into experiments. As you gently approach sleep, take comfort in knowing that discovery is a shared, ongoing voyage. We are, each of us, quietly, sometimes unknowingly, participating in a world-spanning tradition of curiosity. In every question, every quiet moment of wondering, you and the world's scientists alike are linked by the thread of exploration. Now, let's drift to a gentler place still. The land where big ideas inspire not only science, but the imagination, dreams, and creativity that make each night a doorway to new adventures. As your body relaxes more fully, and your mind begins its own gentle drift towards sleep, let's quietly honor a remarkable truth. The very act of wondering about parallel universes stirs something deep within us. A spark not just of scientific inquiry, but of imagination, creativity, and the mysterious theater of dreams. Whether you're a scientist, an artist, or simply someone lying beneath the hush of midnight, the possibility of other realities kindles a refusal to accept limits, a childlike hope that the world may be larger, richer, and stranger than we see by daylight. The idea of parallel universes, multiverses, and other hidden realities has played an outsized role in human culture for centuries. Ancient myths told of shadow worlds and underworlds, heavens layered upon heavens, spaces outside the ordinary that both frightened and comforted. In modern times, these ancient intuitions have found new expression in scientific hypotheses, but they have never lost their capacity to inspire. Writers like Jorge Luis Borges, whose The Garden of Forking Paths imagines every decision branching into countless futures, or Philip K. Dick, who spun universes within universes in his novels, draw directly from these scientific speculations and, in turn, shape how we imagine the possibilities in our own lives. Artists and musicians, too, find fertile ground in the notion of hidden worlds. Painters evoke alternate realities in swirls of color and improbable form. Composers structure music to suggest parallel emotional universes layered atop one another, all echoing the physics of possibility that science gently unfolds. Even our common language, sliding doors, missed chances, what if, reflects the multiverse quietly at play in the human heart. But perhaps the most profound connection between parallel universes and everyday experience takes root in our dreams. Every night, as your conscious mind yields to sleep, your brain embarks on journeys unconstrained by the laws and logic of waking life. In dreams, time may fold, places may shift, and realities branch in a manner uncannily similar to the science of many worlds. Psychologists and neuroscientists have found that dreaming is not merely a quirk of sleep, but an essential process for creativity, memory, and emotional resilience. When you dream, your mind explores alternative paths, rehearsing different versions of reality in the safety of your slumber. Research shows that engaging with complex, mysterious ideas before sleep can even fire the engines of creativity the next day. Albert Einstein, known for his world-transforming equations, often credited imaginative, almost daydream-like states for his most important breakthroughs. The boundaries between science, imagination, and dreaming, it seems, are comfortably permeable. The act of wondering, of staying open to the possibility of more, keeps us both scientifically agile and emotionally whole. So, as you lie quietly tonight, consider this. Your curiosity about parallel universes isn't simply a quest for facts. It is an opening to wonder, compassion, and invention. When you let your questions expand, you give yourself permission to change, to grow, to invent, to dream more freely. The sense that nothing is truly finished or closed, that every choice opens new pathways, is a gentle source of hope. Should you wake in the night, remember, the space your mind travels in dreams is as real in its way as any alternate universe proposed by science. Let this relaxation deepen as you turn your gaze, in imagination, once more to the night sky above. A symbol of infinite possibility, alive with the promise that your smallest wonder may quietly echo across realities greater and stranger than you can yet know. And as we prepare to close our gentle conversation, let's find comfort in the infinite night itself, the most restful reminder of all that is possible, both real and imagined. As you nestle comfortably into your bed, your body still and thoughts gently floating, allow the image of the infinite night sky to quietly unfold above you, a soft ocean of possibility shimmering with silent promise. The night, after all, is the perfect symbol for parallel universes, its endless darkness punctuated by stars, each a potential portal to a new story, a different world, or a reality just out of sight. It is no accident that the nighttime sky has always stirred our primal curiosity about what lies beyond. In every age and culture, people have looked up and felt the gentle tug of mystery, wondering if each star, each subtle haze, might mark the doorway to other universes or secret branches of existence. That sense of wonder is both the beginning and the end of our exploration tonight, because it is the same wonder that fuels both science and dreams. The cosmos stretches so far, so deeply, that if parallel universes do exist, in any of the forms we have whispered about together, they may be unreachable, undiscoverable even with our finest tools. But their possibility transforms our ordinary lives. Each time you gaze at the sky, you are glimpsing a fraction of reality's richness, billions of galaxies, uncountable worlds, endless chances. It is genuinely humbling to realize that your personal story, unique as it feels, is echoed and perhaps even multiplied in ways you can barely fathom. Sleep has its own kind of infinity too. As you descend into its depths, your mind, no longer restrained by the logic of day, drifts on currents that intersect memory, invention, and cosmic mystery. This nightly voyage is itself a quiet metaphor for what scientific curiosity offers, an invitation into unanswered questions, peaceful explorations, and discoveries as subtle as dreams. Whether you find comfort in the idea of other universes, or simply awe at the immensity of our own, this gentle wonder remains a gift, one you can carry through every night, waking rested and a little more connected to the sky above. So, the next time you find yourself awake, listening to the hush of midnight, or looking upward through your window, let yourself feel embraced by the infinity of possibility. There are worlds above you, beside you, and inside you, some real, some imagined, all reflections of the same curious spirit that drew you on this gentle journey tonight. And as your breathing slows and the room grows silent, trust that your questions have reached far, your imagination has soared quietly, and the scientific truths of parallel universes have wrapped you in a peaceful awe. Drift now into the infinite night with its endless potential, and let sleep carry you lovingly, perhaps, into one of those mysterious other worlds.